This is an overview of capacitors, just really briefly, the kind of the headlines of the chapter. And it's just supposed to give you a quick big picture. One way of thinking about it is these are the things that you would want to box on a list of what you walk away with and remember. Just the headlines. So, couple things. First of all, what is a capacitor? And more detail on this in the conceptual picture of a capacitor. But basically, a capacitor is two conductors separated by some space, or an insulator. It's two conductors. And what's special about that is that it's possible to have one of them charged one way and the other charged the other way. And it's a small charge storage device. That's what a capacitor is. It's a little charge storage device. Capacitors don't have to be just two plates like that. They can really be any configuration. They could be, a sphere inside of a sphere, a cylinder inside of a cylinder, as long as we can charge up one and ground the other, and then they're both charged. And actually those three choices, parallel plate and sphere and cylinder, are not picked arbitrarily. Those are actually the only ones that you would need to be able to do very careful computations about. But really, a capacitor could be any. You could have two really wiggly sheets that curve all around, and that could be a capacitor. And it can be lots of shapes. What about the definition of this capacitance? What do we mean when we say capacitance, C? And so here's one really simple equation that you should know and live by and write on your arm with a Sharpie, is this baby. Capacitance is the charge per unit volt, or the charge per volt, where in this situation C is the capacitance in farads, and the Q and the V are the charge on the capacitor and the potential difference between the two plates in the capacitor. By the way, that charge Q, that's by definition, that's the magnitude of the charge on the positive plate, because when a capacitor is charged, the whole thing is net neutral. So when we say the Q on the capacitor, we don't mean the Q on the whole capacitor, we just the charge on the positive plate. By the way, just a little tidbit here, the capacitance farads, if you multiply farads times ohms, you get seconds. Not obvious now why that should be. You can do the dimensional analysis, but pretty soon you'll see why that's important. Just by soon, I mean not in this chapter, but shortly. So anyway, capacitance is Q over V. Actually, if you remember, that's probably one of there are really only two equations here that you really need to know in this chapter, and one of them is C equals Q over V, so remember it. Next big question is how much energy gets stored in the capacitor. We talked about a charge storage device, but you could also think of it as an energy storage device. Capacitors get used for all kinds of things, but one way of thinking about it is that when they're charged, they store energy, and that energy is in the electric field. And so one thing you'd have to remember is how much stored energy, and again, we'll do this in detail, but the stored energy in a capacitor is half of its charge times its voltage. The next question is, what happens when you stick capacitors together? It turns out if you stick capacitors together, you can pretend that they're like one big capacitor. If you put two capacitors together in parallel, like that bottom figure there, you can just add up their capacitance and get the equivalent capacitance of that combination. And if you put two capacitors in series, I bet you the format of this equation looks familiar to you. It turns out if you put two capacitors in series, that the equivalent capacitance goes down, and we'll think in detail about why that is later. What I hope you see right away is that these equations look just like the resistor combination equations, but they're reversed. In series, we use an equation that's like resistors in parallel, and when with capacitors in parallel, we use an equation like resistors in series. So that's like the third big thing to remember. How are we doing so far? Are you counting on your fingers? Three big things to remember so far. Definition of capacitance. Do you remember what it is? C equals, you can do it. Energy stored in a capacitor, U equals half of something. Can you remember what it is? Go back. And the next thing is what happens when we combine capacitors. And the last thing is this: what happens if we put something into the capacitor other than just having a vacuum in between those two capacitors. If we've got a capacitor and it's filled with some insulator called a dielectric, and that dielectric is described by a dielectric constant kappa, the new capacitance is what the original capacitance used to be times the dielectric constant. That's it. That's all there is in the capacitor chapter. Those, I think it was 4 things. And you want to get to the place where even if you can't instantly recreate the conceptual argument for each one of these things, you want to make sure that you know those couple of bottom line things. What's the definition of capacitance? How much energy is stored in a capacitor? What happens when capacitors are combined in combinations? And what happens when you put a dielectric into a capacitor? 4 things. 4 things. Just 4 things.